Welcome. Today, we're diving into the world of cleanroom pressure differentials. We'll explore the science behind it, the engineering challenges, and the compliance standards that keep everything running smoothly. Let's get started with insights from Dr. S.K. Singh, who brings deep expertise to this important topic. Let's talk about pressure differential, a key concept in controlling airflow between cleanroom areas. Simply put, it's the difference in air pressure between two connected spaces. Air always moves from higher pressure to lower pressure. Here, grade B is at plus 35 pascals, and grade C is at plus 20. That means air flows from grade B to grade C. This flow is crucial. It keeps contaminants from moving into cleaner zones, protecting products, ensuring sterility, and maintaining the integrity of the cleanroom environment. Let's dive into the science behind pressure differentials and how they control airflow between rooms. When we create a difference in pressure, air naturally moves from high to low pressure. That's the basic physics at work. Positive pressure pushes clean air out, keeping products safe from contamination. Negative pressure pulls air in, protecting people and the environment from hazards. The pressure gradient, or difference, forms a directional barrier that guides airflow where we want it. For example, a sterile filling room might be kept at plus 35 pascals, constantly pushing clean air outward to block contaminants. Let's talk about why pressure differentials matter so much in contamination control. By managing pressure, we can keep airborne particles like dust, fibers, and process-generated debris from drifting where they shouldn't. It also helps block microbial threats, bacteria, fungi, spores from spreading. Beyond that, pressure control prevents cross-contamination between products, processes, or different manufacturing zones. Ultimately, it's about maintaining a continuous, controlled environment that meets strict regulatory standards. Pressure isn't just air moving, it's a critical line of defense. Let's talk about the benefits of controlling airflow through pressure cascades. By maintaining higher pressure in cleaner areas, we reduce the risk of contamination moving where it shouldn't. This creates a safer, more aseptic environment. For example, in a typical sterile facility, the filling area holds the highest pressure, then preparation, support, and finally the corridor, each step down by a set amount. This pressure cascade keeps the cleanest zones protected, supporting product quality and safety. Let's talk about pressure systems, positive and negative, and how they serve different purposes in controlled environments. Positive pressure systems are designed to protect products by keeping contaminants out. You'll find them in places like aseptic filling or sterile compounding rooms, where the air pressure is higher than surrounding areas to keep everything clean. On the flip side, negative pressure systems work to contain hazardous materials. They're used in manufacturing cytotoxic drugs or handling high-potency APIs, where the room pressure is lower than adjacent spaces to prevent any dangerous particles from escaping. Let's talk about pressure differentials, a key part of maintaining clean and safe environments in pharmaceutical spaces. Here, we see an example where the pressure in a grade B area is 32 pascals, and the adjacent grade C room is at 20 pascals. The difference is 12 pascals, which falls nicely within the recommended range of 10 to 15 pascals. This ensures an acceptable pressure cascade, helping to keep contaminants from moving the wrong way between rooms. Let's talk about monitoring and control systems, focusing on pressure monitoring technologies. We use instruments like differential pressure transmitters, magnehelic gauges, and digital pressure sensors to keep a close eye on conditions. These feed data into control platforms, things like building management systems, SCADA, and environmental monitoring systems. In critical areas, monitoring happens continuously, while support areas get periodic checks. For example, pressure values might be recorded every minute and automatically saved for GMP review, ensuring everything stays within safe limits. Let's talk about pressure excursions and how they can pose risks in controlled environments. Pressure loss often comes from a few common sources. HVAC failures are a big one, things like fan malfunctions, damper failures, or blocked HEPA filters. Then, operational factors play a role. Doors left open or heavy personnel traffic can disrupt pressure. Instrument issues, like sensor drift or calibration errors, also contribute. When pressure drops, the consequences can be serious: reverse airflow, contamination getting in, compromised sterility, and ultimately, impacts on product quality. Managing these risks is critical. Let's talk about alarm management and compliance through automated pressure monitoring. We set clear alert and action levels. For example, an alert triggers when the pressure differential drops below 12 pascals, and an action level kicks in below 10 pascals. When these thresholds are crossed, the system responds instantly with visual and audible alarms, plus email and SMS notifications. Everything logged automatically. Imagine pressure between grade B and grade C falling from 15 to 8 pascals. The system alerts engineering and QA right away, so they can jump on it without delay. Now, let's talk about qualification and validation for the pressure control system. We start with design qualification, where we verify the pressure cascade design itself. Then, installation qualification makes sure all sensors and controls are properly installed. Operational qualification tests the system's limits and alarms, pushing it to its boundaries. Finally, performance qualification confirms the system performs consistently during everyday use. For example, with a specified differential of 15 plus or minus 3 pascals, we observed 14 to 16 pascals during testing, proving the system is qualified and fully compliant. When we control pressure effectively, the benefits ripple across the entire operation. First, it protects the product by reducing contamination risks and boosting sterility assurance. Then, it drives operational excellence, keeping cleanroom conditions stable and cutting down on deviations. On the compliance side, it means better inspection readiness and stronger adherence to GMP standards. Meeting regulatory expectations requires scientifically backed pressure differentials, qualified HVAC systems, continuous monitoring, alarms, and data integrity. All of this ties into a robust contamination control strategy, with regular reviews and requalification to keep everything on track. Pressure differentials are the first line of defense against contamination in pharmaceutical cleanrooms. They work through carefully designed pressure cascades, supported by strong HVAC systems and continuous monitoring. This approach not only protects products and personnel, but also meets strict regulatory standards worldwide. By controlling pressure hierarchies, we guide airflow in the right direction, minimizing contamination risks. Maintaining these systems with robust design and regular checks is key to cleanroom performance, inspection readiness, and consistently producing safe, high-quality medicines. That brings us to the end of our presentation. If you need any further support or have questions, please don't hesitate to reach out. Thank you for your time and attention. It's been a pleasure sharing this with you. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.